Good morning, good afternoon, good evening. This is your Professor Atifreed Mohammed, PhD Artificial Intelligence 830, University of Cumberland's the Lecture12 A3C and Advanced Reinforcement Learning Architectures discussion in this specific lecture. A3C, Asynchronous Advantage Actor Critique, was introduced by DeepMind in 2016 and fundamentally changed how deep reinforcement learning was trained at scale. Before it, most reinforcement learning systems were limited to a single agent collecting experience one step at a time, which made training painfully slow for complex environments. A3C broke the bottleneck by running dozens of agents simultaneously, each in its own copy of the environment, all pushing gradient information to a single shared neural network. The team at DeepMind used A3C to train agents that could play 57 Atari games and navigate complex 3D environments in their DeepMind Lab platform, achieving results that previously took days in a fraction of wall clock time in good hours, using nothing more than a standard multi-core desktop CPU with no specialized hardware whatsoever. This lecture covers 5 connected topics that build on each other in a deliberate sequence. We begin with the A3C is and why parallelism was such a significant advance over prior methods. We then examine the actual mechanism, how workers collect experience, how gradients flow to the global network, and why the design eliminates the need for an experience replay buffer entirely. The third section compares A3C directly against DQN and PPO, so we have clear decision criteria for choosing between them. We then address the real practical challenges of running A3C, variance across training runs, sensitivity to hyperparameters, and compute cost, before closing with the survey of where A3C and its descendants have been deployed in real systems. OpenAI's robotic group used a progression through exactly these concepts when selecting algorithms for their dexterous manipulation work, ultimately evaluating all 3 families of methods before choosing based on the specific constraints of their hardware. This section establishes the conceptual foundation of A3C before we get into the mathematics. The core shift from previous methods is architectural. Instead of asking one agent to sequentially experience the world and update itself, A3C delegates experience collection to many parallel workers while centralizing the parameter updates in a shared global network. This distinction between who collects data and who holds the learned knowledge in what makes A3C scalable. When DeepMind published the original A3C paper, they demonstrated that this approach watched in reality matching or exceeding the performance of DQN on Atari games while requiring dramatically less training time and no GPU, a combination that made method immediately accessible to research groups without access to expensive hardware clusters. The core idea of parallel learning at scale, the central insight of A3C is that experience diversity rather than experience storage. is what stabilizes training DQ and stores a large buffer of past transitions and samples from it randomly to break the correlation between consecutive training examples. A3C achieves the same decorrelation by simply having many agents exploring different parts of the environment at the same time. One worker might be near the start of an episode while another is deep into the difficult section, and their gradient contributions to the global network reflect completely different situations. The team behind Waymo's simulation infrastructure applied an equivalent principle when training driving policies rather than storing and replaying historical driving scenarios. They ran hundreds of parallel simulation instances across different cities, weather conditions, and traffic densities simultaneously, so that any given training batch naturally contained a rich diversity of situations without any explicit replay mechanism. Each worker in A3C is a fully self contained learning agent. It has its own copy of environment, its own local copy of the global network's parameters, and its own short term memory for storing the transitions it collects. A worker follows a simple 4-step cycle: copy the latest global parameters, run for a fixed number of steps collecting states, actions, and rewards, compute the advantage weighted gradient from the experience, and push the gradient back to the global network. Then immediately repeats the number of steps before each push. Typically between 5 and 20 is a key design choice that controls the trade off between gradient freshness and communications overhead. NVIDIA's Isaac Gym platform applies this exact worker model when training robot locomotion policies. Thousands of simulated robots each act as independent workers, running their own physics simulation and computing their own gradient before contributing to a centralized parameter update. The global network shared parameters. The global network is a single source of truth for what the agent knows. It holds the shared parameters that all workers read from and write to. It has two output heads: the actor head, which outputs a probability distribution over actions for each state, and the critic head, which outputs a single scalar estimating the expected future return from that state. Both heads share the earlier layers of the network, which means the feature representation learned by the convolutional or fully connected backbone benefit both the policy and the value estimate simultaneously, making parameter use more efficient than maintaining two entirely separate networks. When Google DeepMind trained agents to navigate their 3D environments called DeepMind Lab, they used exactly this shared backbone architecture, the same convolutional layers, and that recognized walls and objects fed both the movement policy and the value estimator, permitting the agent to develop a richer spatial understanding that served both purposes without doubling the network size. This section moves from concept to mechanism. We examine precisely how gradients flow, why updates can be asynchronous without causing the system to collapse, and what happens when two workers try to update the global network at nearly same time. The mathematical machinery behind A3C is not dramatically more complex than standard actor critique, but the engineering of making it asynchronous and thread safe introduces subtleties, the matter in practice. Researchers at Uber AI Labs, during their work on neural architecture evaluation in the late 2010s, encountered all these implementation challenges when they attempted to scale their RL or reinforcement learning experiments across CPU clusters. They found that getting the gradient, locking, and synchronization exactly right was the difference between a system that trained stably and one that produced inconsistent, irreproducible results. So, this is a quite tongue twister for me. That's a great idea. So, the data flow in A3C has a clear hub and spoke structure. The global network sits at the center. Workers branch outward, each connected to its own environment and one end and to the global network at the other. After collecting experience, a worker computes the gradient of the combined actor critique loss with respect to the local parameter copy and pushes that gradient up to the global network, which immediately applies it. The worker then pulls the updated parameters back down before starting its next rollout, ensuring it is always working from a recent, though not necessarily the absolute latest, versions of the policy. Boston Dynamics used an analogous distributed update architecture when training locomotion controllers for their Atlas robot. Multiple physics simulation instances each computed control policy gradients independently and contributed them to a central parameter server, permitting the overall training process to scale across their internal compute cluster while the central model accumulated improvements from every simulated trial in parallel. A3C, what is called as n-step return, to estimate the advantage of each action where n is typically 5. This means a worker unrolls 5 actual environment steps, collects the real rewards at each step, and then asks the critique to estimate the value of the state reached at the end of these 5 steps. The n-step return is then calculated as the sum of discounted rewards over those 5 steps plus the discounted critique estimate of the final state's value, and the estimated value of the starting state is subtracted to obtain the advantage, which measures how much better the taken action sequence was compared to what the critique predicted on average. Compared to a single step temporal difference update, the 5-step look ahead substantially reduces the bias introduced by an imperfect critique while still being much lower variance than waiting for the entire episode to end. The robotics team at Carnegie Mellon used 5-step return when training their legged robot locomotion policies when A3C style methods, finding that Horizon struck the best balance between credit assignment accuracy and gradient stability across the varying terrain types in the simulation. DQN's replay buffer exists to solve one specific problem. Consecutive transition in a single episode are highly correlated because they represent a smooth trajectory through a single scenario. Now, this is very important. I'm going to repeat it for you so you know why this is profound. DQN's replay buffer exists to solve one specific problem. Consecutive transition in a single episode are highly correlated because they represent a smooth trajectory through a single scenario, and training a neural network on highly correlated data causes it to overfit to the current trajectory, while forgetting that it has learned from others. A3C eliminates this problem structurally rather than mechanically because each worker is at a different point in a completely different episode at any given moment. The gradients arriving at a global network from different workers are inherently uncorrelated without any shuffling or storage required. The practical benefits are significant. DQN's Atari replay buffer occupies roughly 7 gigabytes of memory to store 1 million frames, whereas A3C per worker rollout buffer holds only the most recent 5 to 20 transitions, making the total memory footprint orders of magnitude smaller. The memory advantage was particularly important for the teams training agents at scale on cloud infrastructure, where memory cost per machine directly affects the economics of large training runs. The word asynchronous in A3C precise workers never wait for each other. When worker 1 finishes its rollout and pushes a gradient, it does not check whether worker 2 and 3 have also finished. It simply applies the gradient to the global network and moves on. The worker 1 immediately pulls the updated parameters and begins its next rollout. This means the global network is being updated by whichever the worker finishes first, and the order of updates changes every training run depending on how fast each worker's environment simulation runs. The synchronous variant called A2C removes this randomness by having all workers submit their gradients simultaneously, then averaging them before applying a single coordinated update. A design that is more reproducible and easier to reason about but sacrifices the throughput advantage that asynchrony provides. Google's Brain's large scale distributed training work showed this trade off clearly. Their synchronous training pipelines produced consistent, reproducible learning curves that were essential for comparing architecture variations, while asynchronous pipelines trained faster but required more seeds to obtain statistically reliable results. A3C most valuable properties are its wall clock efficiency and its implicit curriculum. On wall clock efficiency, because workers run entirely in parallel on separate GPUs or CPU cores, in reality on separate CPU cores. Adding more workers directly reduces the time required to collect a fixed amount of experience, and this scaling holds nearly linearly up to around 32 workers. On implicit curriculum, different workers naturally encounter different stages, difficulty levels, and random events in their respective environments, so the global network is continuously exposed to a diverse range of situations without any manual curriculum design. OpenAI demonstrated both properties when training their DOTA 2 agent DOTA by running hundreds of parallel game simulations, each starting from a different game state and involving different hero combinations. Choosing between A3C, DQN, and PPO is not a matter of which algorithm is universally better. DQN and A3C approach the same goal: training an agent to maximize cumulative reward through architecturally opposite designs. DQN maintains a large replay buffer, learns an action value function, and derives a deterministic policy by taking the action with the highest estimated value. This makes it highly sample efficient because each transition is reused dozens of times, but it restricts the methods to discrete action spaces and requires significant memory for the buffer. A3C maintains no replay buffer, learns an explicit stochastic policy directly, and handles both discrete and continuous actions within the same framework. This makes it faster in wall clock time but less sample efficient because each transition is used exactly once. PPO and A3C are both on policy actor critique methods, but their approaches to stability diverge significantly. PPO uses a clipped surrogate objective that mathematically prevents the policy from changing by more than a controlled amount in any single update, and it runs multiple gradient epochs on each collected batch of data, extracting more learning signal per environment interaction. A3C uses no such clipping. Updates are applied directly and can be large, and each batch of data is used for exactly one gradient update before being discarded. In practice, this means PPO produces smoother, more reproducible training curves at the cost of somewhat slower throughput, while A3C trains faster in wall clock time but with higher variance across different random seeds. So Anthropic's training team found this trade-off directly relevant when fine-tuning large language models using reinforcement learning from human feedback. The policy being optimized was a model with tens of billions of parameters, and the clippings in PPO was essentially to prevent a single bad batch of preference data from destabilizing the entire model, whereas an A3C style unclipped update would have been catastrophically sensitive to outliers' reward signals. The architecture of the neural network inside each A3C worker depends entirely on the structure of the state representation the environment provides. For visual environments, anything where the observation is an image or a sequence of frames. A convolutional neural network processes the raw pixel input through several layers of learned filters that detect edges, shapes, and motions before passing the resulting feature vector to the actor and critique output heads for environment with partial observability, where a single frame is ambiguous because the agent cannot tell. For example, which direction an enemy is moving. A recurrent layer such as an LSTM is inserted between the convolutional backbone and the output heads, permitting the agent to accumulate information across time steps and reason about sequences rather than isolated moments. Despite its elegant and historical significance, A3C comes with a set of practical challenges that make it harder to deploy reliably than either DQN or PPO in most modern settings. The three most significant are simple inefficiency relative to off policy methods, high sensitivity to the interaction between hyperparameters, and the difficulty of systematic exploration in environments where rewards are rare or delayed. A3C's three core challenges are distinct in cause but interact in practical. The sample inefficiency arises from on-policy constraint because each gradient is computed from data collected by the current policy. Old data becomes invalid the moment the parameters change, and every transition is discarded after a single use. The hyperparameter sensitivity arises from the coupling between worker count and learning rate. Adding more workers effectively increases the rate of gradient updates to the global network, which changes the optimal learning rate. These two parameters cannot be turned independently. In reality, they cannot be tuned independently, and they turn to a learning rate that worked perfectly with 8 workers will often cause divergence with 32. The exploration challenge arises from the uniform entropy bonus. All workers receive the same encouragement to explore, but there is no mechanism for directing workers toward parts of the state space and have not been visited. So, in tasks with rare rewards, all workers can simultaneously converge on the same suboptimal behavior. A3C was designed in 2016 specifically to run efficiently on multi-core CPUs at the time when GPU accelerated deep learning had become dominant for supervised learning but had not yet been fully adapted for the short rollout lengths typical of on-policy reinforcement learning. One of the most practically significant limitations of A3C is the high variance in its training trajectories across different random seeds, because the order in which workers update the global network is determined by timing randomness that varies from run to run. Two training sessions with identical hyperparameters can produce learning curves that diverge substantially. A3C has had a meaningful impact across three distinct application domains: games and simulation, robotics, and physical control, and autonomous systems. In each domain, the specific properties of A3C, its wall clock speed, its CPU efficiency, and its natural exploration diversity, offered something that alternatively at the time could not. A3C's first major demonstration was on the Atari benchmark, where it matched or surpassed DQN's performance across all 57 games using only a CPU and a fraction of the training time, establishing immediately that the parallel worker approach was viable at scale. Since I have discussed all these uh, pointers in quite depth, so I would strongly suggest you to look at the Legacy and Descendants, the A3C inspired Impala, APPO, and distributed PPO. Its parallel worker design is the foundation of large scale reinforcement learning in terms of training today. So happy learning. See you in the next lecture.